Let's look at the first order integrated rate expression in a little more detail because a lot of people have trouble with logarithms. This is the equation that we had in the last video. This is what we get whenever we apply the calculus to the rate law for a first order process. But there are lots of forms of this based on the rules for logarithms, and this would be an excellent time to review that. If I have the natural log of x over y, just to sort of make it easy, this does not equal the log of x over the log of y. It does not work this way. When you enter this in your calculator, you have to be very careful not to put the numbers in wrong. If I have the natural log of x over y, it does equal the natural log of x minus the natural log of y. This is how logarithms work. This is not how logarithms work. This is how logarithms work. A couple of other things that we can see based on this second expression is that if I have the natural log of x over y, that's the same thing as the negative natural log of y over x. If I flip what's in the logarithm, I change the sign on it. And for that reason, a way that we often see this integrated first order rate expression written is like this. Alright, what I've done is I flipped what's inside the logarithm, and now it has a positive sign. We don't always see the positive sign written explicitly, but now it is not negative kt, it's positive kt. Now, which one of these do you use? Well, it depends. I mentioned earlier that typically the way this equation gets used is you have a problem where you are given 3 of the 4 variables, and there they are the 4 variables: concentration after a certain time period, initial concentration, rate constant, and the time period. So typically the way this problem is worked is you're given 3 of these 4 and you're asked to find the 4th. If you're trying to find the k or the t, if you're trying to find the rate constant or the time period, given both the initial concentration and the concentration after a certain time, and whichever one of these you're not trying to find, whether you start with it in this first form or this second form makes not a whole lot of difference. You just have to be very careful entering this into your calculator. If, however, you're trying to find the concentration at time t, or you're trying to find the concentration initially, then thinking of them algebraically, this first form versus the second form might make a difference. Let me clear some space and then we'll go through the algebra. Alright, in this first expression, let's start here. If I am trying to solve for the concentration at time t, for example, let's say this is my unknown, then I have to get it by itself. In order to get it by itself, the first thing I have to do is get rid of the logarithm that's around it, and that's by taking the inverse natural log. The inverse natural log is usually the inverse function of the log button on your calculator, but mathematically we express it as a little e raised to a power. So the inverse log of a log is what's ever inside the log, the at over a0. The inverse log of negative kt is e to the negative kt. And again, on your calculator, taking e raised to some power is typically the second function of your natural log, and it probably has the little e raised to the x on it. What's your negative sign? Then if I need to take it one step further and solve for the concentration at time t, I can very easily see that there is my formula. So the concentration at time t is equal to the initial concentration times e raised to the negative kt, or the inverse log of negative kt. If instead I'm trying to find the initial concentration, let's say I'm looking for the initial concentration, I could go about the same method here, but it would take a couple of extra steps. Algebraically, it makes more sense to think about this formula, this format I should say. They're both the same formula. This format is my starting point, and solving for the concentration at time 0, or my initial concentration, there I have it. A0 over AT equals e to the kt. This is the inverse log now. It's of the positive kt. And my initial concentration is equal to my concentration at times t times e to the positive kt. And so again, these bottom two formulas are exactly the same formula that we started with, even in the previous video. We've just done some algebra to rearrange them a little bit. Alright, the last thing I want to talk about in this video is going back to both the first order and the second order and looking at that graphical representation a little more closely. So let me get some space. Alright, this was both the first order integrated expression and the second order written in the format of y equals mx plus b. Y equals mx plus b, our line. That means that for a first order process, a plot of the natural log of the concentration versus time gives us a straight line. This happens to be a negatively sloping straight line, and the slope is equal to negative k. A plot of a second order integrated process, a plot of 1 over the concentration versus time, will give us a straight line. In this case, it's a positively sloping straight line, and the slope is equal to k. This is a way to determine whether or not we have a first order or a second order process experimentally. Experimentally, if we are given data, if we are given concentration of our reacting species over various time periods, in other words, somebody is monitoring the reaction and they're making a plot, or they're collecting data of concentration versus time, if we make a plot of the natural log of those concentration values versus time and we end up with a straight line, we can conclude that we have a first order process. If we make a plot of the natural log of concentration versus time and we do not end up with a straight line, if we get a curving line, it's not a first order process. So this might be, depending on the data that you're given, this might be a way to quickly decide if you're talking about a first order process or a second order, if those are your choices. If you're given data of concentration versus time and you plot 1 divided by each of your concentration points versus the time, and you do get this straight line, you can conclude that you have a second order process. If you do not get a straight line when you make this plot, you do not have a second order process. So you might be able to quickly plot the data to determine if you have first order or second order just by looking for which one gives you the straight line. Once you decide that, then this is a way to quickly determine the value for the rate constant by getting the slope of the line. You might not want to do this by hand, but if you've got a graphing calculator, this might be something that you could do quickly, or you could use an Excel spreadsheet to quickly plot this and find the slope of the line.